video is to walk you through some of the things that are helpful to know for Lab 7. Okay, so before we do that, let's rewind back to Lab 6 and discuss what we have so far. We talked about this a little bit in class, but let's go over it one more time. In Lab 6, we had a multiplexer set up where switch 15 controlled one of the 7-segment displays. All right, so if you put the switch in position 0, switch 15 in position 0, then that would tell us to look at these binary digits, and I see that as 1011, which would be hex B. And so what I would expect to show up in the 0 display is a lowercase letter B. All right, and so then if I toggle the switch 15 to position 1, all right, that tells us to select the upper nibble of this 8-bit byte, and that is binary 5, and because this is in switch position 1, I have this set up to turn on this digit and display the hex digit 5. Okay, so that's where we were. All right, what we want to have happen with this lab is we want to take a binary number, and in this case, view it as looking at the whole byte, the whole 8 bits, all right? And we want to convert what that binary number is and display the decimal equivalent, all right? So if we were able to take the binary display and convert this to a BCD format, if we had that in BCD, the BCD could then be used with the multiplexer to drive the digits. I'm not showing all those lines of data flow, but that's the idea. Okay, so in position 0, all right, if switch 15 is, let me clear some things first. If switch 15 is in position 0, then what I want to show is the lower digit. Okay, so if I converted this binary sequence here to decimal, all right, that equivalent is 91. And so what I would want to have happen is when I select the lower bit, I should see the 1 show up here. And then if I select the upper bit, I would see the 9 showing up over here. Okay, so we've already multiplexed the digits in Lab 6. All right, so now what we're seeing is the Bcd conversion circuit lets us display the decimal equivalent with this new result from Lab 7. So that's what we're trying to get to. All right, so what we need to do first is figure out what goes inside this block here that I'm labeling 15 BCD, and then it needs to be 11-bit according to the lab write-up. And we could do it with 8 bits, but we're going to do it with 11 so that we can use any extra bits possibly down the road for other labs. Okay, so what we need to do is talk about this circuit that's going to let us go from hex, a hex representation of a binary number to a BCD representation. Once I have the BCD representation, that lets me show the display in decimal. All right, so this algorithm that we're using here is based on the way you convert binary to decimal. All right, there's a technique known as the doubling method. All right, what we're doing for the BCD is double dabble. All right, we'll talk about the dabble part of that in a second. But with the doubling method, let's just go strictly decimal and do the doubling method. Okay, so with the doubling method, I start with 1, all right, and I double that. So I'm doing all these calculations in base 10. I double that and add, so if I double 1, I get 2, and then I add the next binary digit. Okay, so 2 plus 0 is 2. All right, so I'd have a 2 here. All right. From there, I double the 2. So 2 times 2 is 4 plus 1. This would give me a 5 in this place. 5 times 2 plus 1 is 11. 11 times 2 plus 0 is 22. 22 times 0 plus 1, 22 times 2 plus 1 is 44, plus 1 is 45. 45 times 2 is 90, plus 1 is 91. So that method converts binary to decimal, but all along we use decimal multiplication. And on a digital system, we don't have a way of directly implementing decimal multiplication, so we have to do something else. All right, and that something else is based on some things that you see in your book. If you read the textbook, I believe somewhere in there they talk about if you shift digits to the left, a binary number to the left by one position, that would give you a multiply by 2. All right, so that's not hard to see. If I start with 1 and then I shift that to the left and backfill it with a 0, 1 0 would be 2. All right, if I add another 0, that's 4. Add another 0, that's 8. So every time I'm shifting that to the binary point to the right and the digits to the left, I'm multiplying by 2. Okay. The catch is with a BCD representation, there's some times when you want to carry out into the next nibble. All right, but you have to do something to make that happen. So let me explain with a few examples. Let's start with decimal 5 times 2. Well, 5 times 2 should be 10 in decimal. All right, so I think we're all agreed with that. So the trick here, and I'm just going to show you the trick. What you do is you take 5 and you add 3 to it. All right, so that would be 8. And then if I then multiply by 2, what I get is 5 times 3 is 8. All right, so I'm going to write down the 8. And then if I multiply by 2, I know that I simply add a 0 at the end. Okay? And so the cool thing here is if I look at this, interpret this as BCD digits, this is 10, representing decimal 10. Okay? So that worked for 5. How about, let's try another value. Okay, let's try 4. 4 times 2 is 8. All right, well, if I started with 4 in binary and I multiplied by 2 by adding a digit at the end, that's already good. That's 8. That's what I expected. All right, so I chose 4 and 5 intentionally. That's sort of the threshold of when you have to do this add 3 business, okay? And so the reason we add 3 is that, if you look forward in the book, they talk about BCD addition of 2 numbers, and if the digits are bigger than 5, you have to add 6 to get it to carry correctly. Well, 3 times 2 is 6. All right, so there's a reason this 3 is coming into play. All right, so just to make the point, let's do a couple more. All right, so let me move this over to the side. Shrink this down. Okay, so 7 times 2 is 14 in decimal. But if I take the 7's bigger than 5, to dabble, I need to add plus 3 times 2. All right, so 7 plus 3 is 10, so I write down the 10. Then the multiply by 2 is you add a digit at the end. Okay, so then if I read this off in BCD, this would be a 4, and that's a 1. All right, so you can check all the other combinations. The other ones are left are 7 and 8 and 9, and then the digits less than 4. But that's what we mean by the dabble part of this algorithm. I think technically it should be dabble double instead of double dabble, because you do the doubling after you do the addition by 3. But that's neither here nor there. People call it double dabble. All right, so you only need to dabble if the result is bigger than 5. Okay, so let's talk about how you apply that to a string of binary digits. All right, so in class we'd worked with this same example that, I know in advance, this turns out to be 91 in decimal. All right, so this algorithm is actually doing this double dabble method, which is inspired by, the decimal conversion, where you do all the math in decimal, but this time we're going to do the math in BCD, okay? And so this chart shows you how to do this, and what I'd like you to be able to do is plug in the numbers and see how it works. All right, so let's do that with this case. All right, so I'm going to go with red here. So the first values that show up in register C1. Okay, so I take the bits down. This is a 0 because it just has an initial condition on the C1 register. All right, and then I take 0, 0, 1. Well, that's a 1. Do I need to dabble? No, I don't need to dabble. I just need to double. And the doubling happens because this register is actually shifted, C2 is shifted over. So that shift is occurring at the next stage. So that's where the doubling part comes in. All right, so this is a 1. So we don't do anything. We don't dabble. We just put the 1 right back out. That's not 1. That's 8. Sorry. 0, 0, 0, 1. All right, then we bring this digit down. That's a 0. And so we ask ourselves, what comes into register C2? And so I look at it. That's a 2. Since 2 is less than 5, no need to dabble. All right, so 2 comes on the output. So that's 0, 0, 1. I started in the wrong. Yeah, no, that's right. 0, 0. Sorry. 1, 0. That's 2 coming out of this. That's so frustrating. That's 2 coming out of this C2 register. All right, then I bring this digit down, which is a 1. Let me go ahead and bring all these down. 1, 0, 1, 1. Okay. All right. Let me erase this because that's the conclusion we're trying to reach. All right. Yeah, that's right. Okay, now let's keep going. All right, so in this next stage at C3, I have a 5. I need to dabble. 5 plus 3 is 8. So the output is then 1, 0, 0, 0. All right, and notice C7 is starting to fill up. That's a 0. Bring the 0 down. This is a 1 in it. Okay, C4 is also a 1. Both C7 and C4, I don't need to dabble, so I just repeat the 1. Okay, and so that means coming into C8, I have 2, and to C5, I have 2. Okay, so then I go one more stage. Here, if that's a 2 coming out, this would be 0, 0, 1, 0, and this would be 0, 0, 1, 0. All right, so coming into this register, I now have a 4, and coming in here, I have 1, 0, 1, which is 5. So 5, I need to dabble, so I add 3, and I would get coming out 1, 0, 0, 0. And then for the 4, I have 0, 1, 0, 0. All right, so let me scoot this one down a little bit further, and you can see how everything lines up into the ones and the tens and the hundreds register. Okay, so coming into the ones register, I have 1, and coming into the tens register, I have 9, and coming into the hundreds register, I have 0. Well, that's exactly what I wanted. This is the BCD representation of 91. All right, so by example, I've shown that it's feasible that this algorithm might work. All right, so you could test this for all particular cases and verify that it does in fact always work. All right, and it makes sense. It's mathematically based. You have to do the multiplication in BCD rather than in decimal. And that makes it a little more complicated, but this is the logic, this is the circuitry that does this conversion for you. Okay, so the next part of the lab is you need to actually build these units, the C's. All right, so the C's are the conditional adders. And so we can start with some Verilog, and we know it's 4 bits in and 4 bits out. So by now you should start recognizing where to start. All right, so I'm giving you this, but I think you could have found that. I need to make a module. I need to come up with a name. I need to define the inputs, so I do that here. And then I have to decide whether I'm going to use a procedure or an assignment type of statement. All right, so in this example, I've shown a procedure, and if you remember, outputs need to be registers for procedures, and I have this syntax always, and the sensitivity list is at star, meaning all the variables are included. And then I can come up with a begin-end statement that does an if and an else. All right, and so I'm going to let you fill in that block. If, what would be the condition? Well, I'm looking at the value of n, and I know that on 5 or greater, I'm supposed to do one thing. And on less than 5, I'm supposed to do the other. All right, so you can fill in these blocks on what that should be. All right, so it's not very hard code. You don't have to put together an adder like we did in the past, because Verilog will interpret this procedural block and render it in hardware. Okay, so another way you could do this is with an assignment statement. All right, so this is commented out, but it's another possibility that you could use. So you can assign the output in this case, all right, and it's conditioned on the value of the n register. If n is greater than or equal to 5, then you do one thing, and so the notation would be on the other side of the colon sign. What would you do otherwise? All right, so you can fill in those blocks, and it's pretty easy to make this add 3 block. All right, so the next thing we need to do is take a look at producing the BCD circuitry that does this conversion of the binary representation of a number to the BCD representation. All right, so I'm going to do this I'm going to walk you through the code for a 6-bit version of this, and you're asked in this lab to develop an 11-bit version. All right, so that's a couple of steps involved with that. We'll get to those in just a second, but the first thing you need to be able to do is take a look at the circuit diagram and be able to write a block of code that does the structural code that does this kind of connection for you. All right, so what we know is that each of these blocks are conditional adders, C1, C2, C3. All right, we've already got that designed. All right, and so we're going to define 6 bits coming in, so that's done obviously right here. And then if you look at the bottom, we have 4 bits in the 1 register and 4 bits in the tens register. All right, so I define 4 bits, 1s and 10s. All right, so from there, I need to make some wire assignments, and I'm looking at C1 out. All right, so C1 out are these 4 lines. And so you just need to start paying attention to the notation that indicates which bits go where. All right, so that's the C1 outline, and then I'm going to have C1, I'm going to have the input lines coming in to the first C1 adder. All right, so if you look at the diagram, it looks like the most significant bit, it's 1 bit, and I'm assigning it to a 0. That's this point right here. Okay, and then I'm assigning input lines 5 through 3. All right, so that'd be 5, 4, 3. Okay, those go into the input statement. Now notice how this was done. I'm going to switch the colors. There's these curly brackets that you can use to concatenate vectors together. All right, so you put curly bracket, the vector you want, comma, the thing you want to append. And that puts all 4 bits into the input of that. Oh, I did the wrong register. Okay, the concatenation goes here. All right, so first bit concatenated with these other 3. All right, and then on the output, I'm just sending C1 to the output. That's right here. All right, so then I look at, okay, how do I define C2, the C2 block? All right, so let's erase all this other stuff. Okay, so coming into C2, I have a combination of the C1 outline plus this other input line, so that would be input line number 2. All right, so right here is N2, all right? And then our notation we have would let us pick off those 3 lines. All right, those are the 3 lines coming out of the output register, 2 through 0. Those come in, and again, we have the concatenation with, oh, did I count that wrong? With, oh, I didn't count it wrong, I'm on the wrong line. Okay, so C1 out, 2 through 0, and then input 2 gets concatenated together with the curly braces. All right, so that's put into the input of the next C2 conditional adder. And of course, C2 out comes as the output. All right, so you see what we're doing here. We're looking at the wires, all right? So you look at this next stage coming in, and you have to connect those correctly, including input 1, all right? And then C3 comes out, all right? So once you're done with the conditional adders, you just need to assign the outputs. And remember, 1s was connected to part of C3 and input 0. All right, so that's what I have here on the 1s register. I have C3 out, 2 through 0, and N0. All right, and then I just look at, it looks like the upper bit is always going to be a 0 on the 10s register, and then I just match everything together with this concatenation operation and assign that to the 10s output. Okay, so that gives you an idea of how to construct the BCD circuit. This is a 6-bit version. In the lab, I don't think I included it here, but in the lab handout, there's a 13-bit version that's shown. And then we ask you to do an 11-bit version. So what we're wanting you to do is take a look at the pattern that's shown for generating BCD with this double dabble. And how would you, extend from 6 bits up to 11? Or conversely, you could trim the 13-bit version down to 11. All right, but you would need to make your own diagram. And once you have your own diagram, you can make your own 11-bit version of this code. All right, so that's the next stage. So at this point, we have the conditional adder, and we have the 11-bit BCD circuit that uses that conditional adder. And from here, we need to start putting things all together. All right, so this looks very similar to the code that you did for lab 6, where you had a multiplexer and you have some inputs. But instead of connecting the switches directly to the multiplexers, we're going to have this BCD circuit in between. All right, so the switches get connected to this BCD circuit as the inputs, and then we're taking the 10s and the 1s place to the BCD converter. And so if I put this binary code for 91, all right, on N0, I'm expecting to multiplex out that 1 to the 7-segment display. Okay, and then when I select line 1, I'm getting the 10s place that gets multiplexed out. So that would be a 9 showing up here. All right, so you already have the code for doing essentially, this part of it. All right, where you were connected to the switches instead of through the multiplexer. All right, so you just need to modify that code And when you do that modifications, be sure you pay attention to what you say the file names as, so that you don't get the two modules confused. All right, we had this seg1 from lab 6, and now this is going to be SSEG BCD as the file name for lab 7. Okay, so I think that would, this should do it. Hopefully you understand those steps, and hopefully you understand the operation. Going back to the beginning of this video, if you keep in mind what you're trying to accomplish, you can make that happen. Okay. Along the way, you need to make test benches with expected result tables. This is fairly straightforward to do with the BCD circuits, because you're putting in a binary count, and you should get out on your expected results tables, you should get out the decimal, the BCD version of that. Okay. And so if you showed that on your expected results table, that would give you a good starting point. All right. So pay attention to that. That's an important part of the lab. I got some feedback from the grader that the expected result tables were being a little, cavalierly done, not paying attention to details. And we're going to start insisting on having those be more precise and correct. All right. So hopefully this will get you started on lab 7. They're starting to get more complicated, where you're not likely to finish in just one lab session. You'll probably have to take some of this into the week. And, but hopefully this gives you a nice path forward for accomplishing our goal.